Hi students, welcome back. Today we're going to take a look at the side-side angle triangle congruence theorem to figure out whether or not it is true, or if it is not always true, then maybe hypothesize some of the conditions under which side-side angle will actually produce or generate or convince us that two triangles are congruent. Let's take a look. So just to remind myself what we're doing, I'll make a note and name this point side-side angle. So in order to do this construction, I need to give myself two sides and an angle. So I'll start off with the sides. Why don't we make this side AB and this side BC. And I'll go ahead and name these points. And I need an angle. And why don't we use an angle called A just to make life easy here. So I'm going to do a slightly backwards construction of an angle. Let me show you what I'm going to do. First I'm going to make a circle. And then I'm going to create two rays. And I'm going to hide this circle. I don't actually want to see it. I'm going to hide this point. But I'm going to leave this point here. And the reason I'm doing that is that, ooh, goodness, undo. This point right here will control the width of the angle. So we'll make a little note that says, drag me. And that'll encourage us to experiment around with changing this angle. And we'll call this angle also angle A, right at the end here. So let's give that the name A. So remember that the way we do these constructions is we want to copy the triangle made of angle A, side AB, and side BC. So let's do that construction. In order to do that construction, I'm going to start off by giving myself a line to start with. And I'll hide the two controller points for that line. So that one and that one. And I'll put a new freely moving point somewhere on that line. And the next step is going to be to copy this angle. And I could, for example, measure this angle and try to copy it by typing in an angle. But actually, what I would like to do instead of that is to use the geometric construction for copying an angle. So first, I'm going to give myself a circle somewhere over here. And then I'm going to go ahead and copy that circle using the compass tool. So take that center, take that, and now I have this same circle over here. Next, I'm going to measure the distance on that circle, the length of the chord between these two intersections, and I'll use a segment to do that. And then I'll take my compass tool and translate that distance down here, starting at this intersection. And you'll notice I get another point right here, which is the intersection. I could have done a point down here as well by symmetry, but I'll use the one going up. And I'll draw that ray right there. And I'll draw this ray heading out this way. And I'll go ahead and hide all the things I don't need. Don't need that, don't need that. And I don't need that, and I don't need that. And now what you'll notice though is that my two angles in fact are constructed to be exactly congruent. And just like that, when I move this angle, then my angles stay congruent. When it's a straight angle, we see it's a straight angle. Really interestingly, notice I make more than a straight angle, that it actually bounces back. That's based on how I constructed this. So for angles between 0 and 180, this works. For angles between 180 and 360, that construction will not reproduce the exact same angle. Okay, so there we have the angle A is reproduced somewhere on this line. So the next step, I guess I can hide this line and leave that ray there, is going to be to construct the length AB and then the length BC. So let's call this vertex, why don't we call that A prime, just to keep track that A, the angle over here, is the same as the angle at A prime. So there's A prime. And now let's construct B prime using this distance. So again, we use the compass tool to translate that distance. And that tells us the location of the point B prime right here, using that intersection. And now we're at the most exciting part of this construction, which is we get to look for where is point C prime. So we're going to take the length from B to C and translate that right here, using B as the center of the circle. So again, grab that compass, grab that radius, go to point B, we drop that circle, and now we know that point C is somewhere along this circle. But notice that point C could be here, or C prime I should say, or it could be here. So we could mark, for example, this is C prime right there. But we could also say that C prime is over here. And now we've got a bit of a problem. So I better write this as C prime question, exclamation, question, exclamation, question, exclamation. Because I'm not too sure which of these 2 points should be C prime. And now we see how the side-side angle triangle congruence theorem in fact results in 2 different possible triangles. A prime, B prime, C prime meets these conditions, or A prime, B prime, and the other C prime meets these conditions. Hence my wonderment and exclamation point. There's 2 possible triangles that are created by the side, and the excluded angle. Okay, so now the next question is, well, maybe side-side angle doesn't always work, but are there some conditions when side-side angle actually does work? Could we put some restrictions in place to make this work? And to do that, we could actually explore with our construction. So notice that everything is linked together. If I change this angle up here at A, I also change the angle at A prime. If I change the length of AB, I change the length of A prime, B prime. And if I change the length of BC, I change this length. So a few things that I notice right away are this, that if BC is too short, then in fact we don't get a triangle at all. So this circle, which is drawn from point B prime with this radius of BC, doesn't actually intersect the rays of the angle, both rays of the angle. Second thing I notice is that if we get BC to be big enough, then in fact there's only one intersection right up here, up at C prime. And so this tells me that under this condition, side-side angle actually does work. So right now I'm beginning to notice some trends or some patterns that under certain conditions, side-side angle produces 2 triangles, and under other conditions, side-side angle produces just 1 triangle. There is one more thing to try, which might be changing the measurement of that original angle. And we can again notice that as this angle changes, sometimes we're going to miss the triangle altogether. And sometimes this angle is going to produce for us a unique triangle. So part of your assignment is going to be to investigate these conditions. When and under what conditions does side-side angle produce one unique triangle, or when does side-side angle produce no triangles or at least 2 triangles? That'll be your assignment for this evening.